Hello everybody, this is a hands-on introduction to a project that I call FutureSDR, and it's a very experimental async SDR runtime that has good support for heterogeneous architectures, embedded platforms, so it runs on a lot of devices. And it's implemented in Rust. And in Rust, everything that's async is realized through futures. In other languages, you might know similar concepts like coroutines or promises. In Rust, they are called futures, so they are all over the place, and that's why it's called FutureSDR. And it's really important to highlight that this is experimental at the moment. So it's only basically focusing on the runtime. This is not fully fledged, feature-complete SDR runtime like NoRadio. They're quite the opposite. It doesn't even have basic DSP blocks implemented, for example. Really, the point at the moment is to demonstrate this core concepts and show how the runtime is put together, how you implement blocks, all the primitives you have. Okay, so that being said, let's have a look at the features. It's not an SDR app like GQRX or SDR++ or whatnot. So it's a SDR runtime or framework similar to GNU Radio, POTOS, Red Hawk, Equinox, or the other runtimes. It's implemented in Rust. I really like the language. It's I think for 6 years it was the most liked language from Stack Overflow's survey. It has a good ownership models, good primitives for concurrency, everything very helpful in my opinion here to implement SDR stuff. It has prime support for async environments, and it allows you to specify and come with your own executor. So the executor is not baked into the runtime of the language, like let's say with Go or with Erlang. But in this case, you can really have your own executor that allows us to basically write SDR schedulers that are in essence async executors. We'll later look into that. It's very portable, but it stems basically from Rust, not from me. So it runs on Windows, Linux. There's no reason it shouldn't run on Mac. I have examples for Android. It even runs cross-compiled to WebAssembly in the browsers. This, in my opinion, might be interesting for edge computing. I have an example where I cross-compiled it for Sync platform, so an embedded ARM device, and this is really all working basically out of the box. It's Apache 2 licensed. That basically means there is no GPL dual licensing model to make money or something like this. No, it's basically gives you a lot of freedom. You can even use parts of the code without contributing back. So I think this only has drawbacks for me, let's say, but has more flexibility for people who are interested in the project. Okay, so there's good support for embedded devices. You have a web GUI. The runtime even has a kind of a web server that exposes a REST API that you can then use to interact with the flow graph. Yeah, cross-compilation, I already said that. You have custom schedulers, which are basically these executors for this async runtime, and you have custom buffers, which allow you to directly interface accelerator memory without any double copy issues like NoRadio has. So there you can basically implement your own buffers and then directly write to GPU. And we have examples for Vulkan API or the FPGA. There we have a Sync board that where we have XCDMA drivers to basically get data from and to the FPGA. Okay, so let's have some screenshots. Here it's on Windows. It has a web GUI that I just made for fun with a 3D spectrum. Basically, it's there to show that on Windows you can also use the SOAP drivers and really have hardware support. And here's the Android app. Android supports the Vulkan GPU API. So if you write a program that's running on Linux with using Vulkan, we can just put it on the phone. It works because that's supported by Android. And so in this case, we have here device to host, host to device transfers with Vulkan, everything running on Android. So this is trivial to do. It's here running in the browser. So we have a flow graph you can run on our PC, compile it to native code. You can compile the same flow graph to WebAssembly. And here that's running in Firefox. That's the developer console. Here you have this flow graph. Basically you can watch it executing. Here is a screenshot where it's running on the Sync. Doing this host to device and device to host XCDMA transfers, and just doing something very trivial on on the device itself. I think just adding a number or something like this. Okay, so today what we want to do is, give a bit of a hands-on introduction. So there's an agenda where we look at core data structures in the API. Then, like any SDR framework that I know of, also FutureSDR has these two core primitives, like a stream-based data processing and async message-based data processing. So we start with looking at message-based processing, and then the stream-based processing, like from GNU Radio might you know this work function. Something similar is also here. Can have a look at configuration and logging, the performance, comparing it to GNU Radio. There's custom buffers, so we look at how these custom buffers are implemented for Vulkan and Sync, and then just see the cross-compiled examples. So we just go through them briefly, because I probably will work on more detailed tutorials for Android and WebAssembly. And finally, we can have a look at a flow graph with a web GUI. Yeah, so that's the plan. And let's start with the hands-on part. Okay, so we are now in the project, and FutureSDR is mainly a library that comes with a lot of examples, but there's no real binary. In this case, we just create one, main RS, and it should be picked up by the build system. And I'd recommend you to do the same thing, because FutureSDR is by far not ready to be used as a fixed external dependency. But what you want to do is probably just clone the repository and add your own example or binary like we do now, and play around with this. And if you change something to the runtime and think that's generally useful, you can just open a pull request. Okay, so let's start with some simple project. We use anyhow result, which eases result handling a bit. It's also totally overused on the runtime. And then we can return OK. And that's it. Okay, now we want to use something from FutureSDR. FutureSDR. This is a flow graph and runtime. Okay, so we create a flow graph, and that's kind of the top level data structure for our SDR application. So it contains all the blocks that are connected and stuff like this. And now, instead of kind of running the flow graph like this, like say flow graph run, which would do a lot of things behind the scenes, like spawning threads or I don't know, we create a separate runtime. So, and this is, as I said, basically an async executor. And the runtime allows us now to actually run the flow graph. So hopefully this should already compile. Let's see. That looks good. So obviously the flow graph is empty. So what do you want to do? You run it. It's kind of returning immediately, and then the program finishes. So it's done. But let's think a bit more about the concept of the runtime. So first of all, you might have a runtime and then spawn several flow graphs on it. Or you might make a second runtime that is then used with other cores or whatever, and this runs another flow graph. So this gives you a lot of flexibility in how you want to use your resources, your PC. And as I said, the runtime is an async executor, so you cannot just run flow graphs. You can also spawn async tasks. Let's say spawn async. What can we do? Print line, say hi. And or you can spawn it in the background and forget about the task. And hope that it's fast enough that the hi shows up. Because now it spawns a task in the background on the executor and then spawns the flow graph, which does nothing and immediately exits. Yeah, but it worked. So we can see the hi was printed. Okay, so the runtime allows you to run a flow graph, which is actually just a more complex async function that is called to run this flow graph. And So the flow graph is run by spawning individual tasks for the blocks. And by spawning it on our own runtime, we are able to kind of introspect the topology of the flow graph, see how blocks are connected, and then do something smart. For example, we don't just randomly schedule the tasks or the blocks, but we do it in a way that makes sense. Maybe on one executor, we group adjacent blocks and then call them kind of round robin, so that the samples propagate through the flow graph more or less with a constant fixed latency, for example. All of this is possible by using this approach. If you compare this to spawning operating system threads, then there's not so much you can do, because then you're kind of tied to the operating system scheduler, which will then decide which thread is run when, where, and all this kind of stuff. So you cannot make these decisions. They are made for you. Here you can do whatever you want. Okay, and you have the flexibility of spawning several flow graphs on one runtime. Okay, so the runtime is important, and we kind of only created one default one without any parameters, but actually the runtime can be customized. In this case, it uses the default scheduler, which spawns one thread per CPU that is available to the process, and it doesn't pin them, so they just are free floating, and probably if everything's loaded, they'll distribute to the available cores. And also this scheduler that we use by default, that doesn't look at the flow graph. It just gets these tasks to execute the blocks, and it does it, but doesn't do anything smart with it. We could easily change the scheduler. Let's say we use the small scheduler. It's also the one that's used by default, but we can kind of make a custom configuration for it. Let's call it scat and do a small scheduler new. And now we can define the number of threads, let's say 1. And if we want to pin this thread to a CPU, in this case we don't. So now we should have basically a single threaded scheduler. And instead of creating the default runtime, we create a custom runtime using this scheduler, and we say build because we really use this builder pattern really often. It's a bit widespread in Rust because Rust doesn't support optional or default arguments to functions. So often you have, let's say, a block that has a lot of parameters, complex parameterization with a lot of defaults, and then it's very hard to do that in Rust. So the idea that the pattern that you use is the builder pattern. You create a builder with all the required arguments, and then you can call functions on the builder, allowing you to set optional arguments, and then finally do build. So in this case, we create a builder with a scheduler. This scheduler is a required argument if you do a custom runtime. And then now we could call more functions to set stuff, but we don't need it here, and just immediately create the runtime. And now we have a single threaded runtime. Let's see, how can we easily check if everything is working? Let's say we're at time duration. Let's say instead of exiting immediately, we just sleep here. For a given duration. Say 100 seconds, and we can cancel and Control-C out. Okay, so now we have our custom single-threaded scheduler, and let's run it. Now we should have 100 seconds if it starts. Yeah, let's see if we can find the process. Should have started not with a single thread. It's harder to find. This might. Okay. So we see we have the debug build of the main function, and it has a small scheduler having a small thread So for the small scheduler, there's one worker thread. Okay, now let's see. Can kill it. Now instead of having our custom scheduler, we go back and build the default runtime. Just get rid of it again. So let's forget about this. And we start it now. Unused import. Okay, now you can see we have again cargo run, and in this case we have 12 worker threads corresponding to my 12 cores. Okay, so we already seen that we can easily change the scheduler, change parameters. The small scheduler is this one that I mentioned as kind of the baseline, the default one that doesn't actually look at the flow graph. It just starts all these blocks and then they roam freely, basically. There are also other ones like the flow scheduler, which is a proof of concept for a custom one. We'll look into it later. Okay, so let's go back to our runtime. We saw that we can spawn threads, and now the question is, okay, why are these spawning async tasks? How can it be used? Why might it be useful? And for example, what it allows you to do is, let's say, you want to build a frequency scanner. So let's say you want to iterate and scan a bunch of frequencies. Let's say 1 megahertz, 2 megahertz. I don't know what. And then you iterate over them for cycle. So we just go through it again and again, and maybe, yeah, we could do it infinitely. And then we say, excuse this, setting frequency to okay, so now we would respond this task in the background, and it would exit immediately. So what could we do? There are several options. First of all, we could not spawn this task in the background, but just spawn it and get a handle back. And then we can await instead of running the flow graph. I mean, we can do it just to avoid the warnings, but we can then say async IO lock on handle. So what it does now is it spawns this task on the runtime, and then it goes back, then it spawns this, runs the flow graph, and then to avoid that we finish immediately, we block on this task. We then have to Control C probably. Oh, I already see an issue. Yeah, that is not what I wanted, because that's a busy loop. So what I wanted to do is use the async IO timer and wait a bit. Timer after, let's say 200 milliseconds or so, and then we have to wait it. And we can do this because we are here in an asynchronous context. And I have a okay, let's run it. Great. So we can see it's setting the frequency. It cycles between these two values that we added. So it's doing what we expected it to do. And since there's no exit condition, we have to kill it. Okay, so this already shows how you can basically use this async executor to also spawn your own tasks. And this might maybe be helpful if you do something like a scanner, if you want to interface with a block. Now let's actually build a block to see how you could really set the frequency, how you could interface with the flow graph once it is running. Okay, so For this case, I'd suggest to just build our own custom block that only has a message input. So basically a message handler, and then we can print the messages that it received. And usually these messages could be used to set, for example, the frequency of the device, change tabs of the filter, whatever. So, but I mean, that's not really important here. To avoid typing out everything, there's also a message sync already available. And we can just add it here and adapt it to our needs. Also, it shows you that you can do like script, like to just put in the code in the same file, and yeah, it's not really complex to extend it or make your own small custom blocks. Okay, let's see what we copied from the message sync. It also has a builder. We don't need it. It's too much overkill. So don't need this for the moment. Don't need this. And okay, we can also simplify this a bit. Okay, so let's look at what we actually imported here. The message sync is just a struct, basically just a new type that we define. It doesn't hold any parameters. But we have an implementation for the new function, and it gives us a block. So we can create a block for the FutureSDR. And with FutureSDR, there are two types of blocks. So a block is an enum that is either an async block or a sync block. And this was added because async, we will see, is really nice, gives us a lot of great ways and correct ways to implement I/O and timers and all this kind of stuff. But it might also come with an overhead of running an async function, in particular if you hide it behind a common API surface. So you have an async function on a trade that is associated with overhead during runtime. And if people don't need it, I didn't want to force this overhead on them. So you could always just use async and not await something inside the function, but just calling this async function would result in overhead. So if you don't need any async features, just use a sync block. It has less overhead. To be honest, I didn't do in-depth profiling for it, but as far as I've seen, the overhead of this async is really not too big. Let's see how this develops. Maybe in the future we can just get rid of the sync, keeping it a bit simpler. But for now, we have both options, also to minimize overhead. Okay, so you could also let's see, have my language server reloads maybe. Okay, so the block is an enum, and in this case, we create a block that is async. The only difference is if the work function, so the function that operates on streams, is sync or async. In this case, we just have a message handler, so it totally doesn't make any difference because all these functions that are associated with stream processing, like the work function in particular, we don't really implement. So yeah, if we could just write new sync here and wouldn't make any difference. Okay, so then a block, it has 4 components. It has some metadata that is basically, for example, the instance name of the block, or you can specify if this is a block that has a blocking work function. In this case, it's run on a separate thread to avoid stalling any executor threads, and this kind of stuff. So here's metadata. Then we have all this stream-related I/O. And in this case, we don't add any stream inputs or outputs. We only have the message I/O, and in this case, we register an input. So we have an input handler for this message stuff. And yeah, it has a bit, this is basically a closure, a function closure in Rust. It looks like an overly complex structure, but it's the way it is at the moment to make the borrow checker happy. And yeah, then we have a message handler. And the message handler, all handlers get a PMT and return a PMT. So it's important that the function signature is the same for all handlers. So everyone gets a PMT, everybody returns a PMT. And if you say you have a getter, then you just add a null PMT, a dummy PMT, and are just interested in what you get back. If you have a setter, then you're basically only interested in the thing you run it. Maybe you have set frequency, then you say you wish a frequency and get the one that's actually tuned to. In this case, it might make sense, but yeah, anyway, there's always PMT in, PMT out. These are the message handlers. And PMTs are these polymorphic types that we know from GNU Radio. In FutureSDR, their implementation is that simple. So it's just an enum, and it can be whatever you add here. I didn't kind of think about everything I ever wanted to add, but just added this variants of the enum as I needed them. So there's a string, unsigned integer, 32-bit, double, there's a vector with floats, there's a blob, which is just a vector of bytes. You can just add it here. And if you want, you could, for example, then implement, so just exemplary, I implemented some function like, is this a string? And then it checks, is the enum variant a string? If so, yes. Here you can do toString, and that gives you, if it is a string, it gives you back the string. So it's all that trivial. Or you can parse a string to a variant that you can specify. So I just added some functions to show how easy it is, but yeah. And with GNU Radio, you might know, but PMTs, you can serialize and deserialize them. And what's going on here? And actually, there's a nice crate in Rust that's called SDR. Everybody uses and loves it, and you can just derive serialize and deserialize. And then you have maybe, I don't know, 20 formats, JSON, message pack, flat buffers, everything you can imagine. You can serialize and deserialize it too. I have just a proof of concept, a unit test where it's serialized and deserialized in flex buffers. For this REST API that I mentioned before, I really heavily serialized, deserialized from JSON, as you might imagine. So that all works out of the box without me doing anything. So to get PMTs, I just had to write this. Okay. And here we can see we have the message handler, and it gets a PMT, and we can return it. So we have a PMT as parameter, and with underscore you say that you don't use the parameter just to avoid any warnings. Okay, so now we create a block. The block has the most important thing is here this message input, and that's it already. Maybe I should print something. Print message sync received PMT, and then we print it and just give it back. So okay, this is the simplest block one could ever imagine. So let's just add it to the flow graph. In this case, we have to make the flow graph mutable probably. Add block sync. And we get back the sync. Okay, so this is important. We don't use it. Yes. We create the sync, and then we add this block to the flow graph. If you look at this function, it should, it receives a muted set, and it gets a block. So it really gets the block as a value. Like if you had in C++, I think, a unique pointer. So that means the block is really transferred to the flow graph ownership. So there's no smart shared pointer, and you just get a copy to the flow graph, and then everybody has a shared pointer, and you never know what this guy outside the flow graph starts to call functions while the block is running in the flow graph or whatever. So the block is gone. It's in the flow graph. Everything you get back is an ID, and this is everything we need to address the block inside the flow graph and say, call message handlers on it or whatever you want to do with it. Okay, so we get back an ID. The ID is now in this case probably 0 and describes our block. The block is now in the flow graph. And if we now run the flow graph, we should see that also this doesn't terminate because there's a block in the flow graph and nothing is happening. It's waiting for messages, so it's kind of running infinitely. I hope that it's doing. Yeah, so some warnings because we don't use variables. Okay, we see now the block is in the flow graph and it's, yeah, now just not doing anything. Let's kill it. Now comes the more interesting part. So we cannot just run the flow graph and wait until it completes. This is what this function is doing. We can also say start the flow graph. So that basically puts the tasks with the flow graph and blocks everything on the executor and returns. And what we get back here is a task. So this is the future where we could block on, and we get a handle that allows us to interact with the flow graph. And this is also important because this is what it's called an Ecto Pattern that we use heavily in FutureSDR. And what it means is that the flow graph and all the blocks with their associated tasks, they only communicate through an inbox. So that means there's a channel where they read from several messages, and then this is they act upon this. There are no mutexes, condition variables, strange stuff where blocks block on or wait for. No, they only look at their inbox, and then through this messages that they receive in the inbox, you kind of define a protocol. Like you have messages for connecting buffers. So when the block sees a message to connect a buffer, it does this and that. When a block sees a message that it should run, it runs the work function. All this kind of stuff. When the block sees a message with a PMT that should go to this and that message handler, it sees, let's call the message handler with this PMT, and then it runs the function. And yeah, this is the way FutureSDR works heavily. And in this case, we get the handle, which is an inbox channel to the flow graph, and then this flow graph demultiplexes to the individual blocks if needed, depending on the messages received. Okay, so let's go back. So we want to now call this message handler in our block in our async function. Say spawn background and get rid of this handle. So, and now we have down there, we still then use the task of the flow graph to kind of block the thread and wait until the flow graph finishes. In our case, there is no, will block forever here. And in this other task that we do here, like this frequency scanner, we can use the handle to interact with the flow graph. So we can say handle dot call, and then what do we need? The block ID, which is the sync variable. So the ID that we got back, it's the first handler that we use, and we now need a PMT. Let's say our PMT is the frequency, obviously. Could do it like this. And this is an async function as far as I know. Like this. Okay, now we have a task that, let's comment this out. Then the only thing we should see is that the message sync, so the block inside the flow graph, should receive messages. So we're calling the message handler. Yeah, let's see if this works. If we fix the typos. Yeah. Okay, so we can see now that we are iterating over 1 megahertz, 2 megahertz. We iterate between these two values and send this PMT inside the flow graph, and it calls then the handler of the associated block. So you have to think that none of this is something you'd have to do yourself. You just write your blocks with your message handlers, and the runtime does the rest for you. So you can now access these handlers through calling stuff on the handle. In this case, we just get the PPAC back. Maybe we could, just for demonstration, like git create a new PMT like 32.123. And because now it's a one direction, we just call something. You can also say call back, and then we should get a PMT back, and then we can say received PMT from callback. I can consume it. Okay, let's see what happens in this case. Yeah, now we can see we call the handler and we receive a PMT back, and what we receive back is a U32123. Okay, so far so good. Yeah, if maybe you don't like the way this looks or the handler is there, you could also make the handler a function like my handler, and then have these parameters. Here, and do this in the function. This actually is a result PMT. And then here say register input that calls message sync. My handler. See? This works. Yeah, that's the very same thing. Just a bit refactored, so maybe that looks a bit nicer, I would say. So we have it now as a separate function and not everything inline up there. Good, good. So this is the message sync. We demonstrate now to call these handlers from somewhere external, like every message input you have is automatically exposed to the outside. But obviously you can just do the normal thing like connecting message handlers. We can quickly demonstrate it. Let's say we add a message source, and the project already comes with a message source. Now in this case, we want to actually use it. So use FutureSDR blocks. Let's use the builder to demonstrate the builder pattern again. Because now we can let source as then message source builder. We do new, and now these are the required parameters that we add in here, which is the message that we want to spare the whole time, and then the inter arrival time. So let's say we create PMT U32 and duration, let's say 200 milliseconds on arrival time. And if we now do nothing and immediately build it, we do this infinitely, but yeah, let's just use something that terminates. So in this case, let's say n, how is it called? Messages? N messages 20 messages. Should be 4 seconds. No. Do we have a typo? No, it's called. Yeah. Message. Source builder. That's what we wanted. Auto completion. Bit me. Good. So now it seems to be fine with it, and in this case we also we added to the flow graph source, and now what we can do is we can connect them. So connect message. First one we do is the source in to sync out. And okay, so we can now, let's say we can leave the task here, but maybe it's easier to see if you forget about it. In this case, we don't use the handle. So we start the flow graph and then await it. Actually, the same thing as if we just run it. So do rt run flow graph. And in this case, the source terminates, and then there's a trigger for this flow graph, basically to shut down. Okay, we don't use this. Did I now get it right? Source, out, sync in. Makes a bit more sense if we call it like this. Okay, so now we can see that this is now kind of a separate flow graph. We don't interact with it from the outside. It is just running. It's calling the message handlers, and everything's grand. Okay, so I think for this segment we leave it with this, and then can go over and try some other ways to interact with the flow graph and the message handler. Okay, so this is now where we left off before, and now we want to look into ways to interact with the flow graph from the outside. Could even be on a different PC or whatever. So this is a control board, a remote interface. As I mentioned, there's this integrated web server with the REST API that we have that you can use to interact with the flow graph. Okay, so first thing we do, we can clean up here a bit. In this case, we just want a flow graph that runs for some time. And we could also delete the source again. Having just the sync, then this sync will wait for something to do forever. Okay, so we can clean this up a bit. I guess if we run it now, it shouldn't just do anything. Again, it starts the flow graph, which waits for messages that never arrive. Okay, that's great. And now we want to start the web server, and just have to add it to my config. There's control board enable true, and I can specify the IP just by binding it locally to port 1337. And okay, we now start it again. Should probably see, we see some output here from the web server starting up. Okay, at this point, might make sense to have a look at control port implementation. And this is actually that simple. So we have a start control port, which is called when the flow graph is run. And we have a config for the socket address that is read for the IP. And then we start this, it's based on the Rocket web server. And we just give it manage inboxes. So we give it a copy to all the inboxes of the tasks associated with the block. So this is this Ecto Pattern again. So basically these inboxes give you the ability to send messages to this block or task. And in this case, since you want to call message handlers, you basically you send a message with a PMT telling the block to call the handler of call a particular handler. And this is what we do up there. So we only have, it's just that simple. So we have one road that just tells us how many blocks there are. Then these are the interesting ones. So you can have a GET request to an URL where you indicate the block, then the block ID, the call, and then the call back, the message handler ID. And then everything it does is in this case, because this is a GET request, that means there is no data attached to the request. In this case, it just creates a dummy PMT and calls the handler. And we have the very same thing where we have a post request, and the post request comes with some JSON serialized PMT. So a PMT that we serialized into a JSON, and then it's kind of creating a PMT out of it again, and then calling the handler on it. So this is really everything that is used to implement control boards. So it basically, it creates a back channel. We send async messages. These are this type of messages used by the runtime. We say the block, please here call the callback. It's this handler ID with this PMT as the function argument. And we're waiting for your reply here. Once the reply arrives, we're basically done. We printed it in this case only. Okay. So we give back a string that can then be printed. We could also serialize it back, whatever. So it is just a proof of concept, basically. But it's everything that's needed to interface automatically every handler of every block you will ever write. So this is something you always have to write once as part of the runtime, and then all blocks you create automatically have the possibility to be called through this REST API. Okay, long talk. Let's just give this a shot. What did I say? I think I already started. Local 37 and then API. Okay, so this is the thing that just prints the number of blocks. This was this here, number of blocks, and it just tells you how many blocks are in this flow graph. And what was the other block? 0, callback 0. Oh yeah, now we get a U32.123, and this is exactly what our block is generating when the handler is called. So in this case, we just gave it a dummy value. And we see the reply. Now we could also do something more complex, like a post request, giving it some serialized JSON data. We could have a look here what it got. Message sync received null. So we got a null PMT. Now let's try to give it another type of PMT. And one thing we can do to make a post request is just use curl. Always forget how it's working. Curl here in this case, that's how I figured out how things are working. We tell them to make a post request with this data. So let's just say we want a U32 with 1, 2, 3, 3. Localhost, this is our API, and we use it to call this block. Okay, and then we see it's replying with its default U32.123. And also here we see the block received something from the outside. Or another example, I'm not very good with Python, but there's this request library where I can do the very same thing. You just say post something to this API, again, U32 with 55555, and we now just run that. We get a response okay, and hopefully on this other window we should see this 555. Yeah, so the flow graph received it. So it basically means you can just add message handler to your blocks and they will automatically be exposed from the outside. And you could now just go write a Python script that calls these API endpoints to change frequencies or to change gains or whatever, or get status information from the flow graph and just have a interactive. I mean, all these web libraries, they are very well maintained and easy and accessible, and tons of tutorials with them. So I think it's a very easy way to interact with a flow graph. Okay, so this is for the control part of the FutureSDR. Okay, so we already looked in the message handler. Now we look a bit more in stream data processing. It's the second main way to shuffle data around in FutureSDR. And I thought one thing we could try to implement is a TCP source. So from the message sync, we create a TCP source, and what we don't need any message IO in our case, but now we want to add a stream output. So because we receive data from the socket and output it into an output buffer in the flow graph, so stream it in the flow graph. So we add an output, call it out, and output data with a size of 1. So just bytes. We could also make the TCP source generic over some, I don't know, here, some data type, I don't know, that implements something or so that it receives data like complex or whatever, so that you could have a generic TCP source. But let's keep it simple. We have one that just receives bytes. Okay, and we no longer need the handle, this message handler anymore. But now we are looking into the async kernel. And this is the trait that implements a work function, an init and a deinit function. So these are the most important functions that we have to implement for our block that is doing stream processing. Yeah, as I already said, there are async and sync blocks, and the only difference between these two types of blocks is this word. Init and deinit are always async, we don't really care. But a sync kernel would have a normal work function, and this one has an async work function. The main reason is just for performance reasons. You could use the async function for everything, and you don't have to await something in it. But there's an overhead associated with it, especially in this case, because it's an async trait function. I don't want to go really deep into the details, but there's an overhead implementation associated with calling this function, and this is why there's also a sync version. I don't think that it makes a whole lot of difference, but anyway. And I selected the TCP source because obviously that's a good way to demonstrate async functions, because you can await for accepting the connection and await reading more data from the socket and all this kind of stuff. So let's see how this could look like. Also, a TCP source, implementing a good one is not really easy. Also with GNU Radio, they actually spawn an async framework for this, because the yeah, it's just a nice way of doing it. And they have then the whole GNU Radio runtime and an async runtime running on the side just for this TCP source, and here it just integrates nicely. Okay, so let's have a look. I think first of all, we just print line TCP source deinit, so that we see what's going on, or demonstrate, can better demonstrate what's going on. Here we work. And this is already a complete block that we can use here. So we can use it as a source, TCP source, and add it to the flow graph. Okay, let's see what happens. So let's build it. There's an arrow here, stream IO, not. And we also need work IO, which is part of the function signature. Let's look at it in more detail later. And if we now, okay, looks better. I guess it builds now. And if we run it, we see, oh, runtime error, unconnected output. The thing is that messages can be left unconnected, but streams have to be connected. So in this case, we have an output that's not connected because there's no other block. And for this, we can use a null sync. That's part of the runtime. So part of FutureSDR. So we can use import the block. null sync, and here we can see that the only thing the constructor requires is the item size. So let sync null sync, and he also uses bytes, and we add it to the flow graph. And yeah, then we connect it up. Connect stream. We see we have two. Connect stream with type, where we can define the buffer type. By default, it's just double map tickle a buffer, very same trick that GNU Radio uses. The source, output, sync, volumes, and input. So let's see, does that work? No. I forgot an equals, man. Okay, now we have a block and we start the flow graph. It should be connected. Yeah, and we see a TCP source gets initialized and we call work once, but there's nothing happening. I mean, what should the runtime do? It's just a block that says everything returns true, and then it's not called anymore. Okay, so as I mentioned, we want to use a TCP source and can have a look. Async.NET is a Rust library that is part of this async framework that FutureSDR is based on. And so we can say, I want to have a TCP listener. Just copy paste this here. And now question is, where do we want to open this connection? I'd say we do it during initialization. So that means the block doesn't initialize as long as there is no client connected. And once you connect it, then the flow graph starts up and then you call work. And in work, you can then read from this active connection. Probably if you do a proper full-fledged block, maybe that's not how you would do it, because you want to have the flow graph starts up and then maybe during run when it connects. I mean, it all depends on how you exactly, on the use case or what exactly you want to implement. But let's just go do it here like this to keep things simple and to have a bit of a concise example. So we have a listener. It goes port 88. You have to remember this. Incoming is then the stream of events where I can read next and await it. And here we don't await everything in a loop, but we say if let incoming next await. Here we got the TCP stream, and this TCP stream we assign, we store somewhere in self stream equals TCP stream, and then this writing and all this stuff we will do in the work function. Okay, so obviously it does not yet have this stream, so we added stream as an option of TCP stream, and when we're here we say stream none. Constructor, there's nothing set, and we have to implement TCP stream. Maybe you want to have this where the other imports are. Okay, so the source has a stream and it has some issues stream. Okay, now it seems to be happy. Here we can accept this stuff, and then in the work function, we now want to read from this stream. So what we can do is, let's go back to the example. So this was the listener, TCP stream. Here, there's an example, copy it over. And see what we need. TCP, we already imported it. And then there's a stream. In this case, they connect. Read. This is what we want. Okay, so first of all, we say we want our output buffer. And our output buffer, there's, as you can see, the work function doesn't get any memory pointers or whatever. It gets a lot of variables. For this example, the stream IO is important because from the stream IO, well, let's not call it S, let's call it CO. That's usually what I call my stream IO. So stream IO output 0. And here we want to have a slice. So the output buffer as a slice with the U8, and let's so let out equals, and then we can see, yeah, the output is now a mutable slice of U8s. You could now do all this good stuff with iter over the slice, or I don't know whatever you want to do. All the nice Rust stuff that you can do with a slice. But for now, we don't use a lot. First and foremost, we want to read from this stream. Stream we get from self.stream as mod unwrap. Get it from the option, and then it reads from our output buffer. How can I the out as what can I just do this? Seems to be happy. Okay, and then so we get a number back if n bigger than 0, else. Okay, so if we read from the stream, we await here, we read from the stream and it doesn't get us anything, then if we get 0 back, then it means that we are finished. So the whole client disconnected or whatever, so we won't get any more data from this. So we have to tell the flow graph that we are done. And for this, we use this work IO. And in my opinion, it's an important concept because it's a struct that is there for communicating between this kernel that we are implementing, the work function, and the runtime. For example, we can say it, we are finished. Finished equals true because here the stream basically disconnected. And I think this is very important because, for example, GNU Radio, the idea is like the block does something, the runtime observes this behavior like as a black box, doesn't really know what's going on inside it, and then tries to think of the block is now in this state, so I do this with it, and nothing is really explicit. I think it's better if it's explicit because, in my opinion, GNU Radio tries to solve a problem that's not solvable. Because maybe this block just produces items when it's full moon. How should the runtime know without telling it explicitly, like call me again at this point in time or something like this? So just observing the block and trying to derive something from it don't really work. So the whole idea of this work IO is to be explicit. So in this case, we say, okay, we're finished. Let's see what else we can do with this IO function. So IO, we can also say call again. This is something that tells the block just call work again. The runtime call work again. Even if nothing happens, if it doesn't make any sense for you outside, we want to be called again. Maybe that's just much easier to implement the block or something like this. In our case, we will also do this because once we read something from the socket, we produce the data, and from the perspective of the runtime, because the runtime doesn't know about the socket, there is no need to call again. But we say, hey, just call again. We will then in work read again, do this async read and work again. So here we will say this. And then there's another one that I think is very interesting. That is block on. And this allows you to give the runtime a future and say, hey, only call me again once this future resolves. And now you can put anything in there. You can say, call me again if there's data to read from the socket. Call me again at this point in time or when this timeout occurred. Call me again if there's, I don't know, the file is ready, or whatever you can imagine, you can tell the runtime to be called again at this and that point in time. So let's say async timer after duration from seconds. Wait. So now this would tell you to call me again in a second. Let's just give this a shot. Let's forget about all this and all of this. And if we just have this in the flow graph, do we still import time and duration? I guess it will tell us. No, we don't. Use async timer. Duration. So let's see if it works. So yeah, we don't use all of this at the moment. But it works. So now we created a block that tells the runtime, please call me again every second. And now think about how complicated. So, for example, we could now do message IO post to, I don't know, output a PMT or whatever. And stuff like this is not trivial to do in any SDR framework. And here it's just something that this works out of the box, trivial, and this is just something that looks correct. The correct way to do it, let's say. And by not blocking in work, because we could just issue this timer here as well. So we could just as well do this and not hand over to the work function. And the difference here is if we block in work, then the block doesn't do anything. It will stick in this work function. If we do this block on and return it to the runtime, then the runtime can monitor both events. So it can see if there's a message in the inbox, we will process it and call work. Or even if there are no messages, we will wait for this future to resolve and then call work. So just by using this IO block on, we make sure that we do not we do not stall the block or make it deaf to any external events. Everything will just continue working. I think with this just returning any future is a very powerful and interesting concept. Anyways, let's really try to do some TCP stuff here. So we have the listener. We have, where did we stop? Stream asmod unroad read. We read to the output. If we call again. Probably we should also add a check here. If out.length is 0, so, or does it have something like an empty? Is empty. Then we can return immediately. Let's say then we also don't want to be called again immediately, because then we're really blocked on out, and so we say okay. And then we really wait for an event that somebody read from the buffer, and we can do something meaningful. Return. Okay, so that is it, because also then this n would always be 0, which we then would mistake for it is finished. Anyway, if we have n bigger than 0, we have to tell the output that we consumed, no, we produced items, and we want to be called again. And since the null sync doesn't do anything, and if we don't do anything, then we don't see anything. So what do? We just print whatever we receive. Let's see. TCP received. And string from what do you have? Out 0 to n. Does that work? I'm not sure if we need this. Let's see. Time duration PMT. Oh, it even compiled. That is amazing. Get rid of the warnings. Otherwise, we don't see a lot on our terminal. Okay, so now if we run it, it's initialized. Fancy low. What was it? 8080? Oh, now it's in work. It's running block. Hello world. Amazing. Worked on first try. Yeah, interesting. Okay, so actually that's everything I wanted to show for the stream-based IO. Should give a good, hopefully good first impression, and we'll then have a look more into the custom buffer stuff. Let's see what different types of buffers we can use. Okay, so let's see if we can get a bit of an impression of custom buffers. And when we connect the TCP source with a null sync, then implicitly this created a buffer for this connection. And we can also make this explicit, like with type, maybe not the best name, but it allows us to specify the buffer. Let's say circular. It's the one that we also had. So if I now do circular new, we get a circular buffer. And this is now the same thing as happened already. It now uses the size, buffer size from the config. Let's see. So there's a buffer size 32 kilobyte. That's what it's using. You can also do with size, and we can specify something here. Obviously, that doesn't make sense because the circular buffer allocates memory in multiples of the page size. It has to allocate memory in multiples of the page size, so it will use the smallest size equal or bigger to this value. So probably it would be 4K on my system. Okay, but yeah, this trick doesn't work everywhere. So we also need a different buffer that doesn't rely on this fancy memory mapping and MMU stuff. So we can also use a slab buffer that just uses some memory, very boring. And so we plug that in here, see if it still compiles. And now it's using a different buffer. This buffer, for example, would be used by default if compiled to WebAssembly, a target where we cannot pull this trick with circular buffer. You can also run it, still have this TCP source there, and see localhost 80. I hope it still works. Hello world, looking good. Okay, so we have different types of buffers. Let's have a bit of a look under the hood, because actually this thing here is a buffer builder. So that means we don't instantiate the buffer immediately, but it will then be done by the runtime, because this slab, this data structure here, implements a buffer builder. And then when the flow graph is run, it's calling build, and it's then getting a buffer writer. The writer can be associated with the output port. If we have a look here, the writer only has basically one function to get the reader, the corresponding reader. And it's done like this because there are some buffers that can have multiple readers. For example, the circular buffer, you get the writer and then call add reader as often as you need it. Obviously, it doesn't work for all types of buffers. Anyway, so there's the buffer writer. we can add a reader, and this buffer writer and reader, there are 2 types from it. The one that we used until now is the host type, and with this one provides an API surface that we are pretty familiar with, so that we would expect, like any CPU block probably expects, like having produce, consume, getting the slice for input or output, memory, and stuff like this. So this is a host buffer that has, where all of them have this exact API surface. And then we have the custom buffer, and the custom buffer defines only very limited API, because custom buffer is custom. And I don't think it's really possible to hide any accelerator on Earth behind one API surface. I think you have to be flexible here and then just cast the buffer to the type that you actually expect. So you see there's not a lot of stuff going on here. You can just basically finish the buffer or notify that it's finished and stuff like this. Okay, so you have host and custom buffer. One type of custom buffer would, for example, could be a buffer that for Vulkan, for GPU acceleration. And there's only one trick to it. When you create a connection between a CPU block and the Vulkan block, you use a host to device buffer. Let's have a look. We have an example as part of FutureSDR examples Vulkan. And there we have a flow graph with a source that is just a vector source. We have a Vulkan buffer, and then we have a sink. And basically that's everything. Very simple flow graph. Okay, but for connecting the source to the Vulkan input, we use a Vulkan host to device buffer. And that's the only trick. It creates a pair with a writer and a reader. And the writer has this host API surface, and the reader has this whatever Vulkan thinks that his custom buffers should have. And now you have this edge in between the source and the Vulkan block here that has this host to device reader with its 2 different types of writers and readers. And it's the kind of the opposite is there for getting from the Vulkan buffer back to the device. So in this case, you have a writer that has this custom buffer interface and a reader that has this host interface. So what this means is this vector source block, you can also connect it directly to the sink with a normal circular buffer, because it is expecting something when it writes to its output. It expects a host surface, a host API surface, and it's writing to it, and it doesn't know about Vulkan or anything. But the trick is really that the Vulkan host to device buffer offers a host API surface to this block, and therefore it can just write to this accelerator memory, and that's the whole trick basically. And so we can also have a look at this Vulkan block. So how does it look? Because then let's think about it. It has a work function, and it's from its stream inputs and outputs. It expects them to be Vulkan stream inputs and outputs because it is a Vulkan block. Why should there be a sync input or whatever? So it expects that it is getting Vulkan stuff. Yeah, let's have a look. Here I'm in the work function, and for example, you can see something like here where you get from the CO, you want the first input, and you already see that it's calling a buffers method that is not there. This I here is just a macro that takes the input and casts it to a Vulkan input, basically. And then casting this, it's like a dynamic pointer cast in C++, I think. And then by casting it to this, you can use any API you want. In this case, you get you drain all the buffers that are the GPU buffers that are already full of samples. You launch the buffers to the GPU, and then somewhere at the bottom, once you have this, get back the buffers from the GPU with the processed samples, you just submit it to the output edge. And then on the other side, it will be presented to the host for the vector sync in the example flow graph, and then it will read from it. And it's the very same thing also for the sync implementation. So basically, you are very free to do whatever you want. and in your custom buffers. And to be honest, I don't really have a good idea how to do it else. In particular, I don't think that you should try to have only memory pointers as an interface. So I think there needs to be something else. And that is the approach that I currently have. Okay, that's it for the custom buffer part. So I also wanted to say a few words about configuration and logging. FutureSDR starts with a default configuration that's different for debug and release builds. It then searches in the user level, user home directory, in the folder where you usually configure applications on Linux. So that would be .config, in this case FutureSDR config.toml. If this file exists, it merges it on top. It then looks in the current directory if there's a project config. If so, merges it on top. And finally, highest precedence take environment variables that start with FutureSDR. They are also tried to be parsed and added into the configuration. And then you have in the runtime config submodule, you have a config function that returns the global config. And the config is a struct. It has queue size, buffer size, stuff we've already seen because we configured some of it. For example, we enabled or disabled control board before, we set the log level or whatever. And the interesting part is, I think that this is typed. So for example, this control board bind is parsed to a socket address. That means if I add random nonsense here, it will immediately tell us that the config is broken. So it has to be able to deserialize it into this struct. But at the same time, you don't have to add anything, or you can add what you only the things you want to change from the default config, because it already starts with a complete default config. Okay, but actually the thing that I wanted to highlight is that you can add your custom config on top of that. Let's say you create an SDR application that has a more complex configuration, like some telco stuff or whatnot. So you might also want to deserialize it into a struct and validate it. And this is demonstrated in this custom config example here, where we create my config, a struct, with A, B, C members. A is int, B is string, C is usize, and we derive deserialize property from the 30 crate. We already mentioned this before. And with this, we can now get from the config the my section, or that's with Toml, I think it's called a table. And then we can try to parse that into a my config. In this case, it should work. Example, custom config. Yeah, because what we had in there matches what it expects. Let's open it again, config Toml. Okay, let's say we change A, 1, 2, 3, and rerun this. So now A is 1, 2, 3. If we plug in some, what could we do? Is that even valid Toml? Just let's put in a string. Now I guess it fails. My config could not be deserialized. So this is just a quick demonstration how you could extend the concept. You can also add foo equals var as your config and then try to parse this without creating a struct and deserializing it into this type struct. This is also possible, but I guess especially these custom sections here might come in helpful for some applications. Okay, now let's continue to look at logging. And with Rust, usually if you are a library, you just use the logging macros for debug, warn, error from the log crate. And FutureSDR mainly is a library. So we could say, okay, we just use these macros, and then whoever makes an application out of it should provide this actual logger implementation that is then getting this log message and do something with it, even filter or write it to a file or socket, or just print it on standard out. And but yeah, we wanted to also provide some at least simple logging implementation, because otherwise all these simple examples that we showed before wouldn't have worked. There wouldn't have been any logging output. So what we do is this. at the point when the FutureSDR runtime is started, we see if somebody set a global locker, so if the application already configured login. If so, we don't touch it and just use whatever's there. But if the application did not, we implement, we use our very trivial logger. You can have a look at it. Runtime logging. Here's the implementation. It has a log function, and it just prints FutureSDR, log level, and the message. And during initialization, it sets the max level from the config, so what we specified in the config. And these 26 lines is the whole logging that we use at the moment. But maybe your application wants to do some more fancy stuff, and we have an example for this also included, example logging, and there's a simple flow graph. Let's just run it like this without the custom logger. So now this is what we've already seen the whole time: FutureSDR, log level, and then the message. But now the example demonstrates we set it's called env logger. It's a pretty popular logging crate. I'm not very familiar with it. I just copy pasted this basically from the documentation and set the log level and don't do any fancy setup with it. But in this case, if we rerun it, now it has to recompile, but we should see a different logging output. Okay, so we can see this is a bit more fancy, and FutureSDR says, okay, logger already initialized, we don't touch it. And then we can see here this logger is by default already much more fancy, so it has a timestamp, and again the log level, and it also says from which crate and submodule this log message originated from. So maybe this is handy, and maybe we want to have a much more complex logging setup, so all of this is easily possible. And one more note about logging is that, maybe you're worried, okay, if I add a lot of log message, doesn't this impact runtime performance? And a good thing about the log crate is that you can very easily customize what log messages should be compiled in. For example, you can say, okay, in the debug build, I have excessive logging, but in the release build, I don't want to pay the price for this and have some overhead, even if I maybe do not even use the log messages. So that means not printed, but maybe this still has a runtime overhead and you want to avoid that. And let's see where we have the log rate. It's here. And we can say features max level debug and release max level off. So in this case, we have by default everything enabled in debug mode, and in release mode, we don't have any log messages to avoid any overhead. So in release mode, we just want to, because I use it for performance measurements at the moment. So this is everything I want to say about logging. So the project also comes with some benchmarks, so to evaluate performance, where FutureSDR is compared to a corresponding GNU radio flow graph. And so I have these two measurements, message for message passing and for stream processing. And I don't want to go much into the details, but both measurements are orchestrated through a makefile. You can go into the directory, type make, and everything should run automatically. If you have to interrupt, you can just type make again. It will see which measurements are missing, continue from there, all this kind of stuff. And only thing I wanted to mention is that there are also some kind of setup scripts where you can set the CPU governor to performance, for example. So try to get maximum performance out of it, even though there might still be terminal throttling or whatever, but that's at least the best you can do. Then it creates a CPU set. That means it sets aside a bunch of CPUs, migrates all the processes away from it, and then you have some CPUs only for your benchmarks without a lot of interference from other processes or whatever else might happen on your system. And you also try to migrate or map interrupts to other CPUs. That's not possible for all interrupts, but at least you try. That's it. And here in my measurement, I used CPU 012 and 678. And if I look at, how is this called? Should we look ls? We can see that this is a CPU with a corresponding hyperthread. So that means there's 3 CPUs with a hyperthread or 6 virtual cores or however you want to call it. And I just wanted to highlight it because if you run it on your PC, you might. So this is the thing you want to adjust basically. And yeah, then you just type make, and it will create a message passing flow graphs with higher and higher complexity. So that means first you have only a source and a sink, and then a lot of blocks in between. And then you just see how long it takes to execute the flow graph. So that means it's only measuring throughput, not latency or something like this. So it means you have a fixed amount of data, you want to push it through the flow graph, and you measure the execution time of the flow graph. And yeah, for the message passing, it looks like this. And here we can see that, so we have on the x-axis the complexities or the number of blocks basically, on the y-axis the execution time, and in this case GNU Radio doesn't really perform well, but I mean this is well known that these message handlers are really inefficient, but it's trivial to fix basically. So it's not really interesting. FutureSDR is just faster in this case. Yeah, but it doesn't make a lot of sense to compare that. And what's much, much more interesting is the stream processing. Here it looks like this. Again, on the y-axis and stages, which is kind of complexity or the size of the flow graph, and then the execution time. And here, it makes a lot of sense to look into different schedulers. Okay, so we have GNU Radio as the blue line. They all scale about the same way. So there's no one that's kind of over the top. It looks pretty linear over this range at least. And yeah, so with FutureSDR, we first have the small one. This is the single-threaded scheduler, so it has the worst performance. Then small n, which is the default scheduler, which spawns async workers corresponding to the number of cores available to the process, and doesn't pin them, so they can float around in theory. And this already doing quite well, let's say. And then we have the flow scheduler, and this one tries to group adjacent blocks onto the same worker, keeps them in the local task queue, and goes through this queue in a round-robin fashion. So this is kind of a better schedule, but knowing the structure of the flow graph is kind of a proof of concept, what a better scheduler could do, for example. So yeah, it's performing better. It's not totally over the top. I don't know what it is, 2x, 3x, not too interesting at the moment. The opportunity that would have now to improve it is also try to make the buffer smaller to maybe benefit a bit from caching. When you go through this task round robin on the same core, maybe there's something to gain. I would assume that there is. Another thing that we cannot measure at the moment because we're still working on it, but it's latency. And if you go through the flow graph in the known structure and call all the blocks always again in the same sequence, in the kind of perfect sequence, you should get a lower and much more stable latency. So I hope to be able to show this in the near future. Exactly. So that's it for the performance measurement. Okay, so we've seen that the features we get from FutureSDR, we don't have this to pay a high price for it in terms of getting shitty performance or whatever. Actually, performance is pretty okay in my opinion. Now, finally, I want to step very quickly through some of the more interesting examples in my opinion. One of them is WebAssembly, so we can just compile FutureSDR to WebAssembly and run it in the browser. So in this case, we have a binary that is just running a function, run flow graph. This function is implemented in a library. What it does is it sets up a flow graph that just consists of a vector source, the copy block, and the vector sink. And this vector is filled with random data. We connect it up. We run the flow graph, and then finally we make sure that we received the data correctly. And if we run this on, you see here data matches. But now it was running on my PC. No WebAssembly involved. I have a makefile in the here in this example, and maybe we can already start to build it because probably will take some seconds. So it's now compiling this run flow graph function to WebAssembly. We've seen it had this bind gem which says please make a binding for this function in JavaScript so that we can load the WebAssembly file and call the function. So in the dist folder, we see some WASM files, one of them WASM JavaScript, and we have an index HTML where we have some JavaScript code in it that is loading this WebAssembly file, some async stuff. I have no idea how this works. And is then calling this run flow graph function, which is the function we had this bind gen binding for. Now we do gulp serve in this directory, just spin up a small web server, and now should be able to go to our browser. Most should be okay. Now we have a website that's pretty boring. The more interesting stuff happens in the console. We can see that we just also again can reload. Then we see that FutureSDR is doing stuff here, very verbose, because I was still about to debug the buffer, but now it seems to work. And again, in the finally we say data matches. So, and we have propagated all this data from this random vector into the vector source. So now we have SDR framework running in the browser. I mean, might not seem very useful, but I think WebAssembly is an interesting target, also maybe for edge computing stuff. And in addition to that, there's also Web USB. Some people already have cool demos where they interface USB-based SDRs and get the samples into the browser. And with this, you could then have a full-fledged SDR in your browser. And you could even have hardware acceleration, since there's a Web GPU. And Web GPU, there's a very good Rust crate for this, so we should be rather simple to implement also a Web GPU based block, especially because the API is very similar to Vulkan. So I guess it's pretty easy to implement this GPU acceleration also in the browser. Yeah, but that's still yet to do. So yeah, that is our WebAssembly demo. Okay, so besides this WebAssembly, we also have an example for Android, which I think is interesting. We also have a main RS file to create a binary, and here we only call the run flow graph function, which again is implemented in the library. And in this case, we even use Vulkan. That's a bit the cool thing about this Android example, is that we have portable GPU acceleration. So we create a vector with random data, and we put it in a vector source, have a block to copy it, just because we can, doesn't make any sense. Vulkan block, we have it here. By default, it multiplies everything by 12, and then we have a vector sync. We connect these blocks up using these custom buffers for Vulkan, host to device, device to host. And once the flow graph is run, we make sure that the received data is now multiplied by 12 compared to the original data. And if that's the case, we say data matches. And now I can run it on my PC. And fortunately, data matches, everything's grand. So far, so good. Not more interesting than the Vulkan example. But in this case, we also have mod Android here. And this is something that's only compiled for Android targets. And what we use here is the JNI crate for Java native interface. And this allows or eases creating Android bindings. In our case, we have a function that's called JavaNet Bustable FutureSDR main activity run flow graph. It's a bit weird, but that's the way Android wants it. And we can later see how this path comes together and how it's reflected in our Android app. And everything it does, so this is kind of standard stuff, and everything it does is run the flow graph. That's basically everything. One more thing that might be worth highlighting is in the cargo toml. This project is called Android FS for Android FutureSDR, and we also will create a C dynamic library. So that means if we now compile for Android, we will get a lib androidfs.so that we can then link into our Android application. Okay, so now comes the sad part, because we have to close the editor. For whatever reason, sometimes the builds interfere from the auto-completion and the ARM target. Anyways, so I have here an env script which sets some environment variables, mainly pointing to my NDK, so the Android Native Development Kit. I copied all of this over from when I ported radio to Android, and I guess that's actually not needed, but anyways, just set it. And then my history knows how to compile it. So I have a command where I set Rust flag, so target CPU generic. It's just avoid some warnings. We build the crate and only the library, because building the binary doesn't make any sense, because we cannot run a Rust binary normally on Android. And target, we say ARM64 and target Android. And now we can kick this off, and hopefully that should build and create our lib android.fso. Yeah, and yeah, here I am in this Android Studio where I created a very trivial app. It's in the package net possible FutureSDR. There's a class called main activity, and inside it we have and define an external function runFG. This is exactly this what was reflected in this path in this JNI binding. So it's just the way Java does it, as far as I see. And yeah, we link at the Android FS library, and this one is here with the app. It has a folder for C++ or libraries, external one, so libandroidfs.so. Here I have I made a symbolic link to this build directory of our FutureSDR. So we can hopefully now build this Android application. Already rebuilt, yeah. And can put it on my phone. So now it's starting to install, and probably I have to unlog it and wait until it's installed. One more thing that might be worth mentioning is that since we're using now the Vulkan API, the GPU, you have to indicate this in the manifest Android hardware Vulkan compute. And now the application started. It's absolutely boring, just a black screen saying hello world. More interesting stuff hopefully is happening on the console. We scroll up a bit. Yeah, so we have FutureSDR runtime. We see some logging output. Here, all from this host to device, device to host, vector sync terminating, data matches. So here the flow graph finished, and it everything worked as expected. So now we have FutureSDR SDR flow graph that uses the GPU, and it runs on my Linux PC. You can run it on Windows. You can, I think, also Raspberry Pi is a Vulkan API. My Android phone is a Vulkan API, and all of this is portable. I think it's pretty nice to see that this works. Yeah, that's for Android. Okay, so the final example I want to show targets a sync board, and now switch scenes. I waited for this so long. Yeah, this is a Xilinx ZCU 106 board with an MP SoC chip. I have no idea. It has an ARM cores together with an FPGA, and it's running a small Linux system on the ARM, and just running FutureSDR on this Linux system on the ARM is trivial. So the interesting part here is obviously interfacing the FPGA, and that's what we are doing. We create a flow graph and have some random data, put it in a vector source, copy it. Here we have the sync block on the FPGA. We got a vector sync to get it back on the host. We connect it up, this time with custom buffers for host to device, device to host for this FPGA stuff. So this is interfacing DMA engines. And yeah, once we got the data back, we make sure that what I wanted did on the FPGA was actually applied. So in this case, the IP block only adds 123 to a number because that matches my FPGA skills. And yeah, so I don't want to go into much detail here how this is working, because I have this way too long blog post about exactly this. And here I tell about this board and how I put it together. I think there I have my trivial IP block that adds 123 to a number. I click around in the GUI until I have some hardware design. I also have a video about it just to see the whole process. And then I create a Pedal Linux distribution that's also from Xilinx, minimal Linux distribution. Also there, I don't do anything fancy. It's basically going through the tutorial from Xilinx. The only thing I basically adjust here, or I do that might be notable, is I use the device tree to pre-allocate some DMA buffers. And I also do everything with user space IO. So that means the DMA engines instantiated on the FPGA, I don't interface them through the Xilinx DMA driver, but I tell it through the device tree, say, hey, use the generic user space IO driver for it. And then I can just in user space, I mean, everything I want to do there is kind of set some registers that are mapped to some physical addresses, but I don't know the physical addresses in my user space process. And everything that this user space IO basically allows me to do is translate between this virtual address space in my user space process and the physical address where this DMA registers are mapped to. So this is all of this is described here. And in the context of FutureSDR, what's very interesting is that through this user space driver, it's very easy to have both, like blocking operation. I can block until I receive the DMA buffer back. And this is done basically through reading from a file descriptor. Or I can also have an async interface to it by polling the file descriptor and waiting until it's readable. So it really integrates well with all these async stuff. But again, it's all in this blog post, and you can have a look if you're interested. Okay, so we have this flow graph, and there is a script that compiles it. Sync sh, and probably it's already built. Yeah, we can have a look at this script. There is no magic here. It's just, again, one of these commands like I had one for Android build, cross build, example sync, target arch. In this case, it's a Linux GNU system. And we want to have the sync feature because this also gives us this custom buffers. That's everything we have to do. Then cross compiles. And now we can copy it over. Where are we? We need to go to target, arch, debug, example. Okay, now we see here's where the binary landed, and we can now copy it to the target. Sync binary 106. Just put it in the root directory, and okay, now it's starting the transfer. Okay, be done soon. Here I have a shell. Oh, it's already there. Is it already done? And we have the binary here in the root. Execute it. And it's a lot of this debug output again from host to device, device to host drivers. Sync stop to vector sync terminating. Everything has worked because we in the end we have this certs where we go through the thing. So if it doesn't panic, then everything worked as expected. So that's it for this sync example where we use FutureSDR to even interface FPGAs on this embedded device. And now in this embedded device, obviously it is really cool to have this control port interface because now it's the beginning. I didn't intend to do that, but here it even started the web server, so we could already control it through this if the flow graph was running longer. So this is, I guess, an example where this REST-based API really is great. Okay, so last thing we want to do is have a look at the GUI. Okay, so since this is supposed to be an SDR, I figured maybe we want to sample something. And in this case, I have a Tcp source and an RTL SDR connected to my PC. Tcp wraps different SDR drivers, including the one for the RTL SDR. So we have a source block for it, then pipe it to an FFT, calculate the spectrum, calculate the magnitude, and then stream all of this into a WebSocket sync. At the moment, this is how I do my GUI. So I just stream it to a WebSocket sync, and then there's a separate thing that reads the sync and displays the data. And it doesn't necessarily have to be a web-based thing, but at the moment I do it mainly in the web. It's obviously cool for embedded targets, but I also do it here on when I use it on my PC. So let's start this example. You see it initialized the RTL SDR. It starts this web server thing, and can go to our browser, localhost. We already seen this API endpoints, where now we see again the number of blocks. And we could now do something like, what do we have? Block 0, callback 0, try to come up with a post request to this endpoint to set the frequency of the SDR, of the SOAP SDR block or whatever. But obviously that's not how I want to do it. And this is where the front end directory here comes into play. It's a separate kind of subcrate in there, and it includes a lot of components to interface FutureSDR flow graphs. And as you might have expected, this is again implemented in Rust and will be compiled to WebAssembly, which can then be instantiated through JavaScript. Much fun. For example, we have this folder with control port. Here we have components like calling a message handler, polling it periodically, having radio buttons where you can say, when you can choose one of the options and then send the corresponding message, or you can use a sliders where we use mainly now in the following. And for example, this, I don't want to go into the detail how this is working here. It's called URS. It's very similar to React, just in Rust. And the cool thing is that we can implement the web-based GUI using our PMTs and all our types that we defined for FutureSDR. So there's no disconnect here. Everything is typed. Everything is in Rust. And yeah, that's the advantage here. Maybe the easiest thing is if we look at an example. So we have the same thing for GUI. So at the moment, only time representation and frequency representation, which is a waterfall plot. That's everything we have. And even those are just a proof of concept without auto-scaling, without fancy features. Yeah, and with a library, we can export, for example, functions to JavaScript if we want to do that. For example, I have wasm bindgen to export a function that says add slider, and this would then instantiate a slider component. And then whenever you slide, it would kind of issue a post request sending the slider value to the message handler endpoint. So for example, we have here the block and callback, and say we want to send a PMT with U32. And these are the slider min, max, and step values. And we have similar stuff here. We add a frequency, so this waterfall plot, and this waterfall plot just wants a string with the WebSocket endpoint that it can connect to and stuff like this. So yeah, this is what we're doing in Rust world. So these functions, and here we have another example where we have a whole app. So you can kind of decide, you can create bindings to instantiate separate components and then do your application, everything in JavaScript, the business logic, let's say. Or you can create complete applications in Rust world. Then this is similar to React, where you have different components that are nested. And this is just showing you how you would mount such a more complex app consisting of multiple components. All is just for demonstration. This is not really well fleshed out. In the assets folder, we have the corresponding websites. Let's look at index.html. It's just, it's loading. Here it's doing it our wasm.js. So it's loading this Rust stuff compiled to WebAssembly. And when it's loaded, it has all these functions that we just saw available. So it can call this add frequency. It can call add slider. It can mount the app. And in this case, the frequency to this diff with the ID frequency, we mount the waterfall plot that is reading from this WebSocket. And you have to keep in mind, all this ugly stuff in the front end, these components, you don't have to implement them because somebody will implement them. And then you can only create your website with something like this. So I need a frequency plot, I want a slider, and this and that. So this is kind of the, let's say, how a user would create its website. And you would assume that all these functions were already made, all these control port components, somebody implemented them. Okay, so now we have this, that's the index.html website. We will see a waterfall plot, a slider, and then the app, which kind of demonstrates some of the available components. Yeah, let's see what happens. So if we now don't go to the API endpoint, but just go to the main website, we get this index.html website served, and here we got a waterfall plot. Pretty boring. At least it's using WebGL, so it should provide us a decent performance when we get some more data. Here at the bottom we have a slider. This slider is then using PMTs. We can see U32 PMT with a value 851 megahertz. So we're now kind of scrolling around in the spectrum. I think somewhere at 800, there's some LTE carrier, and at 811 we can see, so that's an LTE carrier that we see, and this is here NB-IoT carrier. This just right beside the normal carrier. So this demonstrates how you can use slider. And so this is exactly this website that we had here. The frequency is the waterfall plot, the slider is the slider. And all this other stuff down here comes from the app. For example, we have something radio button, so we can 811 we already are. We can go to 100 megahertz, submit. Now it's sent. It issued this post request. It's tuned to 100 megahertz, so these are now FM stations probably, and can go back, and then we are here again at 800 megahertz. So this is just some very, very simple demonstration of the GUI components that you can build. And obviously this is the most ugly thing you might have ever seen. But now with some CSS, some very simple CSS, you can build a much more fancy interface. And as the name suggests, lol.html, it's not really meant seriously, but you can just add some background, and yeah, then you have some more fancy stuff in here. You go back to 11, probably should see the LTE carrier again. And yeah, in the web, you can just goof around, do whatever you want. And I've seen a demo from Google where they did a 3D visualization from audio spectrum, and I just adapted it here to have a 3D visualization of the spectrum at 811 megahertz, where we again see parts of the LTE carrier with the NB-IoT having a 3D spectrum in the browser. Yeah, and all of this, so going from this very simple one to this more fancy looking stuff is, I mean, maybe 20 lines of CSS. So all of this is pretty trivial, and it's just to give you a bit of an idea of what you can very easily build even in a browser. Okay, so that was the not so brief introduction to FutureSDR, and I hope you like it. I hope you give it a try, and I'm really curious what you think about it. Okay, bye.